Question 1. The evaluation methodology shows that a client wishes to upgrade the lighting in a multi-story office building to modern LED fixtures to improve energy efficiency and reduce operating costs. The existing electrical infrastructure, including panel boards and branch circuits, was installed several decades ago. What is the most professional and compliant approach for the certified electrical contractor to take? Option A. Recommend the most advanced and energy-efficient LED lighting system available, regardless of the existing electrical infrastructure's capacity or the client's budget, as energy savings are paramount. Option B. Immediately proceed with the installation of the new LED lighting system, assuming the existing circuits can handle the reduced wattage of LEDs compared to older technologies. Option C. Conduct a detailed load calculation and capacity assessment of the existing electrical system to determine if it can safely accommodate the proposed LED lighting load, and then present compliant upgrade options to the client that balance energy efficiency with budget and infrastructure limitations. Option D. Advise the client that upgrading to LED lighting is too complex and costly given the age of the electrical system, and suggest replacing existing fixtures with standard incandescent bulbs to minimize disruption. The correct answer is C. Conduct a detailed load calculation and capacity assessment of the existing electrical system to determine if it can safely accommodate the proposed LED lighting load, and then present compliant upgrade options to the client that balance energy efficiency with budget and infrastructure limitations. Explanation. Scenario analysis. This scenario presents a common challenge for certified electrical contractors, CEC, in commercial office buildings, balancing the need for modern, energy-efficient lighting with the existing electrical infrastructure and budget constraints. The challenge lies in interpreting and applying relevant codes and standards to a practical situation where cost-effectiveness is a significant factor for the client. A CEC must not only understand the technical requirements, but also the client's objectives and the limitations of the existing system. This requires a nuanced approach that prioritizes safety and code compliance while also delivering value. Correct approach analysis. The correct approach represents best professional practice because it prioritizes a thorough assessment of the existing electrical system's capacity and the proposed lighting system's energy demands. This aligns directly with the fundamental principles of electrical safety and code compliance, such as those found in the National Electrical Code, NEC, in the U.S. Specifically, it ensures that any upgrades do not overload existing circuits or panels, which is a critical safety concern. Furthermore, by considering the client's budget and the long-term operational savings of energy-efficient lighting, the CEC demonstrates a commitment to providing a solution that is both compliant and economically viable, fostering client trust and satisfaction. This approach embodies the ethical responsibility of a CEC to provide safe, reliable, and cost-effective electrical solutions. Incorrect approaches analysis. One incorrect approach involves immediately proceeding with the installation of the new LED lighting system without verifying the capacity of the existing electrical infrastructure. This is a significant regulatory and ethical failure. It violates the NEC's requirements for ensuring that electrical installations do not create hazards due to overcurrent or inadequate capacity. Ethically, it exposes the client to potential risks of electrical fires, equipment damage, and service interruptions, and it demonstrates a lack of due diligence and professional responsibility. Another incorrect approach is to recommend the most expensive, cutting-edge lighting technology solely based on its energy efficiency ratings, without considering the client's budget or the feasibility of integrating it with the existing electrical system. This approach, while seemingly focused on energy savings, fails to address the practical and financial realities of the project. It can lead to cost overruns, project delays, and client dissatisfaction, and it neglects the CEC's duty to provide solutions that are appropriate for the specific circumstances. It also risks recommending a system that the existing infrastructure cannot support, leading to further complications and potential code violations. A third incorrect approach is to dismiss the client's request for energy-efficient lighting due to perceived complexities or potential cost increases, opting instead to simply replace existing fixtures with standard incandescent bulbs. This fails to meet the client's stated objective and misses an opportunity to provide a modern, cost-saving solution. It also demonstrates a lack of proactive problem-solving and a failure to advise the client on best practices and available technologies, which is part of a CEC's professional obligation. This approach prioritizes convenience over client benefit and potentially leads to a less efficient and more costly long-term solution for the building owner. Professional reasoning. Professionals should employ a decision-making framework that begins with a comprehensive understanding of the client's needs and objectives. This is followed by a thorough assessment of the existing conditions, including the electrical infrastructure's capacity and condition. Next, the CEC must identify all applicable codes and standards, e.g., NEC local building codes, and determine how they apply to the proposed work. The evaluation should then involve exploring various technical solutions, considering their compliance, safety, cost-effectiveness, and alignment with client goals. Finally, the CEC should present a clear, well-reasoned recommendation to the client, outlining the rationale behind the chosen approach and any potential implications. This systematic process ensures that decisions are informed, compliant, and in the best interest of the client. Question 2. The audit findings indicate a pattern of confusion regarding the hierarchy of rules within the National Electrical Code, NEC, and the role of informational notes. Specifically, some project documentation suggests that certain installation practices were based on the content of informational notes as if they were mandatory requirements. This raises concerns about the contractor's fundamental understanding of NEC structure and organization. Which of the following represents the most appropriate approach for an electrical contractor to ensure compliance with the NEC when interpreting its organizational structure? Option A. Treat all content within the NEC, including informational notes, as equally mandatory requirements to ensure the most comprehensive level of safety and compliance. Option B. Focus primarily on the sections of the NEC that are most frequently cited in previous audit reports, assuming these represent the most critical areas for compliance. Option C. Rely on the interpretations and practices of other contractors in the local area, as their experience generally reflects the accepted standard for NEC application. Option D. Prioritize and strictly adhere to all mandatory rules found in the articles and sections of the NEC, using informational notes solely for supplementary understanding and clarification of intent, and consulting the authority having jurisdiction if any ambiguity persists. The correct answer is D. Prioritize and strictly adhere to all mandatory rules found in the articles and sections of the NEC, using informational notes solely for supplementary understanding and clarification of intent, and consulting the authority having jurisdiction if any ambiguity persists. Explanation. The audit findings indicate a recurring issue with the interpretation and application of NEC, National Electrical Code, structure and organization, specifically concerning the hierarchy of rules and the use of informational notes. This scenario is professionally challenging because a contractor's understanding of these foundational organizational principles directly impacts compliance, safety, and the efficient execution of electrical installations. Misinterpreting the NEC structure can lead to incorrect design choices, code violations, and potentially unsafe conditions, all of which carry significant legal and financial repercussions. The correct approach involves a thorough understanding of how the NEC is organized, recognizing that mandatory rules are found in the articles and sections, while informational notes, often preceded by informational note or note, are advisory and do not impose requirements. Best professional practice dictates that electrical contractors must prioritize and adhere to the mandatory rules within the NEC. This ensures that installations meet the minimum safety standards established by the code. Relying on informational notes as mandatory requirements or ignoring them entirely when they provide crucial context for understanding mandatory rules are both failures in professional judgment. An incorrect approach would be to treat informational notes as mandatory requirements. This is a regulatory failure because informational notes are explicitly designated as supplementary information, not enforceable rules. They are intended to provide background, explanations, or suggestions, not to create new obligations. Another incorrect approach is to disregard informational notes entirely, even when they clarify the intent or application of a mandatory rule. This can lead to misinterpretations of mandatory rules, potentially resulting in non-compliant installations. Ethically, this demonstrates a lack of diligence in understanding the code fully, which is essential for ensuring public safety. The professional reasoning process for similar situations should involve a systematic approach to code interpretation. When encountering a code requirement, the contractor should first identify the mandatory rule. Then, they should consult any associated informational notes to gain a deeper understanding of the rule's intent and application. If there is any ambiguity, seeking clarification from the authority having jurisdiction is the most prudent step. This process ensures that installations are not only compliant with the letter of the code, but also with its spirit and intent, prioritizing safety above all else. Question 3. The control framework reveals that a certified electrical contractor is overseeing the installation of a new electrical system in a commercial building. During a site inspection, the contractor notices that a conduit run has been installed slightly differently than depicted on the approved electrical drawings, though it appears to be functionally sound, and does not immediately present an obvious safety hazard. What is the most appropriate course of action for the certified electrical contractor? Option A. Continue the installation but make a note to address the conduit deviation during the final inspection phase to minimize disruption to the current workflow. Option B. Inform the site supervisor of the deviation and instruct them to correct the conduit run to precisely match the approved drawings, regardless of potential delays or costs. Option C. Proceed with the installation as is, assuming the minor deviation will not impact overall system performance or safety, and document the deviation for future reference. Option D. Immediately halt work on the affected section and consult with the project engineer or client to obtain clarification, and if necessary, revised approval for the deviation before proceeding. The correct answer is C. Proceed with the installation as is, assuming the minor deviation will not impact overall system performance or safety, and document the deviation for future reference. Explanation. This scenario presents a common challenge for certified electrical contractors, balancing the need for efficient project completion with strict adherence to safety regulations and client specifications. The challenge lies in identifying potential deviations from approved plans that could compromise safety or functionality, even if they appear to offer a shortcut or cost-saving measure. Careful judgment is required to discern between minor, inconsequential modifications and those that necessitate reapproval or pose a risk. The correct approach represents best professional practice because it prioritizes safety, compliance, and contractual integrity. By meticulously comparing the installed work against the approved electrical drawings and specifications, the contractor ensures that all work meets the required standards and the client's expectations. This proactive verification process is a cornerstone of responsible electrical contracting, directly aligning with the ethical obligations and regulatory requirements to perform work safely and competently. It also serves as a critical step in risk management, preventing potential future issues, liabilities, and rework. An incorrect approach that involves proceeding with installation without a thorough comparison to approved plans is a significant regulatory and ethical failure. It demonstrates a disregard for the established design and approval process, which is in place to ensure safety and functionality. This failure can lead to noncompliance with electrical codes, potential hazards for occupants, and contractual disputes with the client. Another incorrect approach, such as assuming minor deviations are acceptable without verification, also constitutes a failure. This assumption bypasses the due diligence required of a certified professional and can result in hidden defects or code violations that may not be immediately apparent but can have serious consequences later. The professional decision-making process for similar situations should involve a systematic review of all project documentation, including approved plans, specifications, and any change orders, before commencing or continuing work. A thorough comparison of the actual installation to these documents is essential. If any discrepancies are identified, the contractor must immediately halt work on that section and consult with the project engineer or client to determine the appropriate course of action, which may involve obtaining revised approvals or correcting the installation. This iterative process of verification and communication is fundamental to maintaining professional standards and ensuring project success. Question 4. The audit findings indicate that a flexible cord used to supply power to a portable industrial equipment in a manufacturing facility appears to be a general-use cord, and the auditor questions its suitability for the specific application due to potential exposure to oil and abrasion. As a certified electrical contractor, CEC, what is the most appropriate course of action to address this finding? Option A. Inform the auditor that all flexible cords are rated for general use and that as long as the cord is intact, it is acceptable for the application. Option B. Assume the auditor is mistaken and proceed with the project without further investigation, as the cord is functioning correctly. Option C. Replace the cord with any readily available cord of similar gauge, as the specific type of flexible cord is not critical for this type of temporary power connection. Option D. Consult the National Electrical Code, NEC, specifically Article 400, to determine the appropriate types of flexible cords permitted for the identified application and environmental conditions, and verify if the installed cord meets these requirements or if a replacement is necessary. The correct answer is D. Consult the National Electrical Code, NEC, specifically Article 400, to determine the appropriate types of flexible cords permitted for the identified application and environmental conditions, and verify if the installed cord meets these requirements or if a replacement is necessary. Explanation. This scenario presents a professional challenge because it requires the Certified Electrical Contractor, CEC, to interpret and apply specific code requirements for flexible cords and cables in a practical, on-site context, balancing safety, code compliance, and project efficiency. The auditor's findings highlight a potential deviation from established standards, necessitating a thorough understanding of the National Electrical Code, NEC, as adopted and enforced within the relevant jurisdiction for CECs. Correct approach represents best professional practice because it directly addresses the auditor's concern by referencing the specific NEC articles governing the use and installation of flexible cords and cables. This demonstrates a commitment to code compliance and safety, which are paramount for a CEC. By identifying the relevant sections, e.g., Article 400 for flexible cords and cables, the contractor can accurately assess the situation, determine if a violation exists, and implement the necessary corrective actions. This proactive and code-centric response ensures the electrical installation meets the minimum safety standards, protecting both personnel and property, and upholding the integrity of the profession. An incorrect approach that involves dismissing the auditor's findings without a thorough code review is a significant regulatory and ethical failure. It suggests a lack of due diligence and a disregard for established safety standards. This could lead to unsafe installations, potential hazards, and legal liabilities. Another incorrect approach, such as assuming all flexible cords are interchangeable regardless of their listing or intended use, violates fundamental NEC principles. Flexible cords are specifically designed and listed for particular applications, and using them outside their intended scope can compromise their insulation, strain relief, or overall integrity, leading to electrical failures or fire hazards. Furthermore, failing to consult the NEC or relevant manufacturer's instructions when in doubt is a direct contravention of professional responsibility and a failure to adhere to the established framework for electrical installations. The professional decision-making process for similar situations should begin with a clear understanding of the auditor's specific concern. The next step is to immediately consult the applicable sections of the NEC and any relevant manufacturer's installation instructions. This involves identifying the type of flexible cord or cable in question, its application, and the environment in which it is installed. A thorough comparison of the existing installation against the code requirements and manufacturer's guidelines is crucial. If a discrepancy is found, the professional must then determine the appropriate corrective action, which may involve replacing the cord, reconfiguring the installation, or documenting why the current installation is compliant if the auditor's interpretation was mistaken. Maintaining clear documentation of all findings, consultations, and corrective actions is also a critical aspect of professional practice. Question 5. The performance metrics show that a recent installation experienced an unexpected power outage affecting multiple circuits during a minor ground fault. As the certified electrical contractor responsible for the installation, what is the most critical factor to investigate regarding the coordination of overcurrent protection devices, OCT, to prevent recurrence? Option A. Confirmation that the ampere ratings of all OCT are appropriately sized for the connected loads according to the National Electrical Code. Option B. Assessment of the cost-effectiveness of the selected OCT to ensure the project remain within budget. Option C. Verification that the time current curves of upstream and downstream OCT exhibit sufficient separation to ensure selective tripping for all credible fault currents. Option D. Examination of the physical installation of the OCT to ensure they are securely mounted and properly wired. The correct answer is C. verification that the time-current curves of upstream and downstream OCT exhibit sufficient separation to ensure selective tripping for all credible fault currents. Explanation: this scenario presents a professional challenge because it requires the certified electrical contractor, CEC, to interpret and apply complex coordination requirements for overcurrent protection devices, OCT, in a real-world installation. The challenge lies in ensuring that the chosen OCT will selectively trip, isolating faults to the smallest possible area without unnecessarily interrupting power to other parts of the system. This involves understanding the interplay between device characteristics, time-current curves, fault current levels, and the overall system design, all while adhering strictly to the applicable electrical code. Professional judgment is crucial to balance safety, reliability, and cost-effectiveness. The correct approach represents best professional practice because it prioritizes safety and code compliance. By selecting OCT that demonstrate proper coordination, the contractor ensures that in the event of a fault, only the OCT closest to the fault will operate, thereby minimizing disruption and preventing cascading failures. This aligns with the fundamental principles of electrical system design and protection as mandated by the electrical code, which aims to protect both personnel and equipment. An incorrect approach that fails to consider the time-current characteristics of upstream and downstream OCT would be a regulatory failure. This could lead to non-selective tripping, where a higher-rated upstream breaker trips for a fault that should have been cleared by a lower-rated downstream breaker. This violates the code's intent for selective coordination, potentially causing widespread power outages and compromising safety. Another incorrect approach, such as relying solely on device ampere ratings without verifying coordination, ignores the critical time element of OCT operation. This is a failure to apply the code's requirements for protective device coordination, which is essential for a safe and reliable electrical system. A third incorrect approach, prioritizing the lowest cost OCT without verifying their coordination capabilities, is an ethical and regulatory failure. While cost is a factor, it cannot supersede the paramount requirements for safety and proper system protection as defined by the code. Professionals should use a decision-making framework that begins with a thorough understanding of the project's electrical system design and the specific OCT involved. This involves consulting the manufacturer's data for time-current curves and fault current calculations. The next step is to systematically evaluate the coordination between each upstream and downstream OCT pair, ensuring that the downstream device operates before the upstream device for all credible fault conditions. This process should be documented and verified against the requirements of the applicable electrical code. If coordination cannot be achieved with standard devices, alternative solutions or further system design adjustments should be considered. Question 6. Stakeholder feedback indicates a need to optimize the selection process for raceway systems in a new industrial facility that will house various manufacturing processes, some of which involve corrosive chemicals and others are designated as potentially hazardous locations. The project manager is seeking the most efficient and code-compliant method for determining the appropriate raceway types for different areas. Option A. Rely on the raceway manufacturer's general product catalog to identify suitable options, assuming their products are universally applicable across different industrial environments. Option B. Prioritize raceway types that are generally less expensive and quicker to install, assuming they will meet the basic requirements for conductor protection. Option C. Select raceway systems based on the preferences of the installation crew, as they have extensive practical experience with various materials. Option D. Consult the National Electrical Code, NEC, for permitted raceway types based on environmental conditions, application, and specific location classifications, and then verify compatibility with conductor types and installation requirements. The correct answer is D. Consult the National Electrical Code, NEC, for permitted raceway types based on environmental conditions, application, and specific location classifications, and then verify compatibility with conductor types and installation requirements. Explanation. Scenario analysis. This scenario presents a common challenge in electrical installations where multiple raceway types are considered for a single application. The professional challenge lies in selecting the most appropriate raceway system that not only meets the immediate installation requirements, but also adheres to long-term safety, durability, and code compliance. Misinterpreting or overlooking specific code provisions related to raceway types, their applications and installation methods can lead to unsafe conditions, code violations, and increased maintenance costs. The need for deep understanding of the National Electrical Code, NEC, is paramount. Correct approach analysis. The correct approach involves a thorough review of the NEC, specifically Article 300, wiring methods and materials, and relevant articles for each raceway type being considered, e.g., Article 358 for uparantu and us conduit, Article 314 for outlet, device, and pull boxes. This approach ensures that the chosen raceway system is permitted for the specific environment, e.g., wet location, corrosive atmosphere, hazardous location, provides adequate physical protection, and is installed in accordance with all applicable code requirements. It prioritizes safety and compliance by grounding the decision in established electrical codes, which are designed to protect persons and property. Incorrect approaches analysis. One incorrect approach is to select a raceway based solely on cost or ease of installation, without verifying its suitability for the environmental conditions or its compliance with NEC requirements for the specific application. This fails to address potential issues like corrosion, physical damage, or inadequate support, which can compromise the integrity of the electrical system and create safety hazards. Ethically, this is a failure to uphold the duty of care to the client and the public. Another incorrect approach is to assume that a raceway permitted in one location or application is automatically suitable for another, without consulting the NEC. For instance, using a raceway suitable for dry indoor locations in a wet or corrosive environment would lead to premature failure and potential electrical hazards. This demonstrates a lack of due diligence and a disregard for the specific requirements outlined in the code for different environmental conditions. A further incorrect approach is to rely on past practices or personal experience without cross-referencing current NEC provisions. Building codes and standards are updated periodically to reflect new technologies and safety findings. Adhering to outdated practices can result in non-compliance with current safety standards. This is a regulatory failure and an ethical lapse in maintaining professional competency. Professional reasoning. Professionals should approach raceway selection by first identifying the environmental conditions, the type of conductors to be installed, and the specific application. Then, they must consult the NEC to determine which raceway types are permitted for that specific set of conditions and applications. This involves understanding the limitations and advantages of each raceway type as defined by the code. A systematic review of relevant NEC articles, cross-referencing with manufacturers' installation instructions, where applicable, and considering the long-term performance and maintenance aspects will lead to the most appropriate and code-compliant solution. Question 7. The audit findings indicate that a recently installed motor circuit for a critical piece of machinery is experiencing intermittent tripping during startup, despite the overcurrent protection device appearing to be sized correctly based on the motor's full load ampere rating. The contractor responsible for the installation is seeking guidance on the most appropriate course of action to address this issue, while ensuring full compliance with the regulatory framework governing certified electrical contractors. Option A. Install a time delay fuse with a rating equal to the motor's full load ampere rating to address the tripping issue. Option B. Advise the client that intermittent tripping during startup is a normal characteristic of some motor installations and no further action is required. Option C. Replace the existing overcurrent protection device with one that has a higher ampere rating to prevent nuisance tripping during motor startup. Option D. Consult the motor manufacturer's documentation and the applicable electrical code to determine the correct type and rating of overcurrent protection required for motor circuits, considering both starting current and overload conditions. The correct answer is C. Replace the existing overcurrent protection device with one that has a higher ampere rating to prevent nuisance tripping during motor startup. Explanation. This scenario presents a professional challenge because it requires a certified electrical contractor to interpret and apply specific overcurrent protection requirements for motors, as mandated by the relevant regulatory framework for the Certified Electrical Contractor (CEC) exam. The challenge lies in understanding the nuances of motor protection beyond simple circuit breaker sizing, considering factors like starting current, continuous operation, and the potential for damage to the motor itself. Careful judgment is required to ensure compliance and prevent potential hazards. The correct approach represents best professional practice because it directly addresses the specific requirements for motor overcurrent protection as outlined in the applicable electrical code. This involves selecting protection devices that can handle the motor's high starting current, while still providing adequate protection against sustained overloads and short circuits. Adhering to these code provisions ensures the safety of personnel, the protection of equipment, and the reliability of the electrical system, all of which are fundamental ethical and professional responsibilities of a CEC. An incorrect approach that fails to account for the specific needs of motor protection, such as using standard branch circuit protection without considering motor characteristics, represents a regulatory failure. This could lead to nuisance tripping during motor startup, or worse, failure to trip during a sustained overload, potentially causing motor damage or fire. Another incorrect approach might involve selecting overcurrent devices based solely on the motor's nameplate full load current without considering the code's allowances for higher momentary currents during starting, which could result in undersized protection that trips unnecessarily. Ethically, this demonstrates a lack of due diligence in applying the code to protect both the equipment and the system. The professional reasoning process for similar situations should involve a thorough review of the applicable electrical code sections pertaining to motor circuits. This includes understanding the definitions of overload and short-circuit protection, the specific rules for sizing conductors and overcurrent devices for motors, and any exceptions or special conditions. A contractor should then assess the motor's characteristics, e.g., horsepower, voltage, service factor, and the type of load it serves to select the most appropriate protection method and device. Consulting manufacturer documentation for the motor and the protection devices is also a critical step in ensuring proper application and compliance. Question 8. Stakeholder feedback indicates a concern regarding the grounding electrode system installation for a new commercial building addition. The existing building has a metal underground water pipe electrode and structural steel that is effectively grounded. The new addition's electrical service is being installed with a new ground rod. The electrical contractor is considering whether to bond the new ground rod to the existing water pipe and structural steel, or to consider the new ground rod as a standalone electrode for the addition. Option A. Rely solely on the existing metal underground water pipe as the grounding electrode for the new addition, and do not install the new ground rod. Option B. Bond the new ground rod to the existing metal underground water pipe and the structural steel to create a single, interconnected grounding electrode system. Option C. Install the new ground rod and bond it only to the new building addition's electrical service grounding electrode conductor, but not to the existing building's grounding electrode system. Option D. Install the new ground rod as a standalone electrode for the new addition, without bonding it to the existing water pipe or structural steel. The correct answer is B. Bond the new ground rod to the existing metal underground water pipe and the structural steel to create a single, interconnected grounding electrode system. Explanation. This scenario presents a common implementation challenge where conflicting interpretations of grounding electrode system requirements can arise, particularly when dealing with existing structures and new additions. The professional challenge lies in ensuring compliance with the National Electrical Code, NEC, while also addressing the practicalities of integrating new grounding components with older systems, all while maintaining safety and functionality. Careful judgment is required to balance code requirements with site-specific conditions and stakeholder expectations. The correct approach represents best professional practice because it prioritizes a thorough understanding and application of the NEC's grounding electrode system requirements. Specifically, it involves identifying all permissible grounding electrodes present and ensuring they are bonded together to form a single, effective grounding electrode system. This approach adheres to NEC Article 250, which mandates the interconnection of all grounding electrodes to provide the lowest impedance path to Earth, thereby enhancing safety by effectively dissipating fault currents and lightning surges. It also demonstrates a commitment to diligent work and professional responsibility by proactively addressing potential code violations and ensuring the integrity of the electrical system. An incorrect approach that involves solely relying on the new ground rod without bonding it to the existing water pipe and building steel is professionally unacceptable. This failure constitutes a direct violation of NEC 250, 52A, and 250, 58, which require the bonding of all accessible grounding electrodes. Ethically, this oversight compromises the safety of the installation by creating a fragmented grounding system, potentially leading to dangerous voltage differentials during fault conditions or lightning strikes. Another incorrect approach, which is to assume the existing water pipe is sufficient and ignore the new ground rod, is also a regulatory failure. While the water pipe may qualify as a grounding electrode, NEC 250-53D2 requires supplemental electrodes when the water pipe electrode does not have at least 10 feet in direct contact with the earth. Furthermore, failing to bond the new ground rod to the existing system, as per NEC 250-58, negates the benefit of the new electrode and creates a less effective grounding system. The professional reasoning process for similar situations should involve a systematic review of the NEC, specifically Article 250, to understand the requirements for grounding electrode systems. This includes identifying all available grounding electrodes, understanding their bonding requirements, and ensuring that the installed system provides the lowest practical impedance to earth. When encountering existing conditions, a thorough site assessment is crucial to identify all existing grounding components. If there is any ambiguity or conflict with code requirements, consulting with the authority having jurisdiction (OJ) is a critical step to ensure proper interpretation and compliance. Question 9. Governance review demonstrates that a recently completed commercial building's electrical installation utilized rigid metal conduit (RMC) throughout. Upon inspection, it was noted that some conduit runs appeared to have a higher density of conductors than typical. A few junction boxes contained fittings that were not clearly marked with a testing laboratory's label, and the spacing between conduit supports in certain horizontal runs exceeded the maximum distances specified in the NEC. Considering the impact on system safety and code compliance, which of the following represents the most critical wiring method and material concern that requires immediate attention and correction? Option A. The spacing between conduit supports in horizontal runs exceeding NEC specifications. Option B. The general use of rigid metal conduit as the primary wiring method. Option C. The observed higher density of conductors within certain conduit runs. Option D. The presence of non-listed conduit fittings in some junction boxes. The correct answer is D. The presence of non-listed conduit fittings in some junction boxes. Explanation. This scenario presents a common challenge for certified electrical contractors, balancing the need for efficient installation with strict adherence to safety codes and material specifications. The challenge lies in identifying subtle deviations from approved wiring methods that could compromise the long-term integrity and safety of the electrical system, even if the immediate functionality appears unaffected. Careful judgment is required to distinguish between minor aesthetic imperfections and potential safety hazards or code violations. The correct approach involves a thorough understanding of the National Electrical Code, NEC, and the specific approved wiring methods and materials for the given application. It requires the contractor to verify that all installed components, including conduit fill, support methods, and junction box types, comply with the NEC's requirements for the environment and load. This ensures the system is not only functional but also safe, durable, and compliant with legal and industry standards, thereby protecting the client, the public, and the contractor's professional reputation. An incorrect approach would be to overlook the use of non-listed conduit fittings. The NEC mandates that all electrical equipment and materials used must be listed and labeled by a recognized testing laboratory for their intended use. Non-listed fittings may not have undergone the necessary safety testing and could pose risks such as inadequate grounding, poor mechanical protection, or fire hazards. Another incorrect approach is to accept conduit that is overfilled beyond the NEC's specified percentages. Overfilling can lead to overheating, insulation damage, and difficulty in future maintenance or modifications, all of which are safety concerns and code violations. Finally, failing to ensure proper conduit support at the required intervals, as specified by the NEC, can lead to physical stress on the conduit and conductors, potentially causing damage and compromising the integrity of the wiring system. Professionals should approach such situations by first consulting the relevant sections of the NEC pertaining to the specific wiring method being inspected. They should then systematically verify each component and installation detail against these code requirements. If any deviation is found, the contractor must identify the specific code violation and determine the appropriate corrective action, which may involve replacing components or reconfiguring the installation to achieve compliance. This systematic, code-driven approach ensures that all installations meet the highest safety and performance standards. Question 10. Cost-benefit analysis shows that using a smaller gauge conductor than the National Electrical Code, NEC, requires for a specific circuit load would significantly reduce material and labor costs for a new residential installation. The client is aware of this and has requested the contractor proceed with the smaller gauge wire to stay within budget. As a certified electrical contractor, CEC, what is the most ethically and professionally responsible course of action? Option A. Suggest using a cable type not rated for the specific environmental conditions of the installation to offset the cost of the smaller conductor, as long as it appears functional. Option B. Agree to the client's request to use the smaller gauge conductor, citing the cost savings as a primary benefit and assuming the risk of potential future issues. Option C. Omit the grounding conductor for the circuit to significantly reduce material and labor costs, as the client is prioritizing budget over perceived safety features. Option D. Explain to the client that while the smaller gauge wire is cheaper, it does not meet NEC requirements for safe operation under the expected load, and therefore the installation must use the code-specified conductor size to ensure safety and prevent potential hazards like overheating and fire. The correct answer is D. Explain to the client that while the smaller gauge wire is cheaper, it does not meet NEC requirements for safe operation under the expected load, and therefore, the installation must use the code-specified conductor size to ensure safety and prevent potential hazards like overheating and fire. Explanation. This scenario presents a common ethical dilemma for a certified electrical contractor, CEC, where a client requests a deviation from standard practices for cost savings, potentially compromising safety and long-term reliability. The challenge lies in balancing client demands with professional responsibility to adhere to codes and ensure safe installations. The correct approach prioritizes safety and code compliance above immediate cost savings. This aligns with the CEC's ethical obligations and regulatory requirement to install electrical systems that are safe for occupancy and use, and to prevent hazards. Adhering to the National Electrical Code, NEC, or applicable local codes, even if it means a higher upfront cost, represents best professional practice because it ensures the installation meets minimum safety standards, is insurable, and avoids future liabilities and potential hazards. An incorrect approach that accepts the client's request to use a smaller conductor size than specified by code for the given load is a direct violation of the NEC. This failure is regulatory because it breaches the mandated safety standards designed to prevent overheating, fire, and equipment damage. Ethically, it demonstrates a disregard for the client's safety and the safety of future occupants. Another incorrect approach, suggesting the use of a cable type not rated for the specific environmental conditions, e.g., damp or wet locations, to save money, also constitutes a regulatory and ethical failure. The NEC specifies cable types based on their intended environment to prevent insulation degradation, corrosion, and electrical faults, all of which pose significant safety risks. Ignoring these specifications compromises the integrity of the installation and exposes the client to potential hazards and code violations. A third incorrect approach, agreeing to bypass a required grounding conductor to reduce material and labor costs, is a critical regulatory and ethical lapse. Grounding is a fundamental safety feature designed to protect against electric shock by providing a path for fault current. Its omission creates a severe hazard, directly violating core safety principles of the NEC and demonstrating gross professional negligence. Professionals should employ a decision-making framework that begins with understanding the client's needs and budget. However, this must be immediately followed by a thorough review of applicable codes and standards. If a client's request conflicts with these requirements, the professional must clearly explain the code mandates, the associated risks of noncompliance, and the reasons why the requested deviation cannot be implemented. The professional should then offer compliant alternatives that may achieve some of the client's cost-saving goals without compromising safety. Transparency, clear communication, and an unwavering commitment to code compliance and ethical conduct are paramount. Question 11. System analysis indicates a dwelling unit renovation is underway, involving the replacement of existing receptacles and the addition of new lighting circuits in bedrooms and living areas. The existing electrical system was installed prior to current FSI requirements. The client has expressed a desire to keep costs down and questions the necessity of installing arc fault circuit interrupters, FSI, in these renovated areas, stating the original wiring was safe. What is the most appropriate course of action for the certified electrical contractor? Option A. Install FSI on all new and replace circuits serving bedrooms, living rooms, and other areas specified by the current NEC for FSI protection, explaining to the client that code requirements mandate this for new work and modifications. Option B. Install FSI on all circuits, regardless of location, to provide the highest level of safety, even if not explicitly required by the NEC for all areas. Option C. Install FSI only on the new lighting circuits, as these are considered new additions, and use standard breakers for replaced receptacles. Option D. Install standard circuit breakers for all new and replaced circuits, informing the client that the original wiring did not require FSI and that the renovation does not necessitate them. Correct answer is A. Install FSI on all new and replace circuits serving bedrooms, living rooms, and other areas specified by the current NEC for FSI protection, explaining to the client that code requirements mandate this for new work and modifications. Explanation. This scenario presents a common challenge for electrical contractors, balancing code compliance with client requests and the practicalities of existing installations. The professional challenge lies in accurately interpreting and applying the National Electrical Code, NEC, requirements for arc fault circuit interrupters, FSI, in a renovation context, where existing wiring may not have originally required FSI. The contractor must ensure safety while also managing project scope and client expectations. The correct approach represents best professional practice because it prioritizes life safety and adherence to the most current applicable code. NEC Article 404, 4 and 406, 12, as well as informational notes, generally require FSI in specific dwelling unit locations. When a renovation or modification occurs, the NEC often mandates that the new work or modified areas comply with the current code. Therefore, installing FSI in the specified locations during a renovation is a direct application of these safety standards, protecting occupants from fire hazards caused by arcing faults. This proactive stance on safety, even when not strictly mandated for the original installation, is a hallmark of a responsible and ethical electrical contractor. An incorrect approach that fails to install FSI in the required locations during a renovation is a direct violation of NEC requirements. This failure to comply with the code constitutes a regulatory failure, potentially leading to unsafe conditions and liability for the contractor. Ethically, it represents a dereliction of duty to protect the client and occupants from known electrical hazards. Another incorrect approach that involves installing a standard circuit breaker instead of an FSI in a location requiring FSI protection is also a regulatory and ethical failure. This bypasses a critical safety device designed to prevent fires. A third incorrect approach that involves installing an FSI in a location not explicitly required by the NEC, while not a direct code violation, could be considered a misallocation of resources or an unnecessary expense for the client if not justified by a specific risk assessment or client request. However, the primary concern in this scenario is the failure to install FSI where they are required by code during renovation. The professional reasoning process for this situation involves 1. Thoroughly understanding the current NEC requirements for FSI, particularly as they apply to renovations and modifications. 2. Clearly communicating these requirements to the client, explaining the safety rationale and any associated costs. 3. Documenting the code requirements and the client's decisions. 4. Prioritizing life safety and code compliance above all else, even if it means pushing back on client preferences that compromise safety. Question 12. Benchmark analysis indicates that a common point of confusion for electrical contractors relates to the precise meaning of terms used in the National Electrical Code, NEC. When planning an installation involving multiple interconnected components designed to deliver electrical energy, which of the following NEC definitions most accurately describes the overall arrangement? Option A, an enclosure. Option B, a circuit. Option C, a system. Option D, a raceway. The correct answer is C, a system. Explanation. This scenario presents a professional challenge because it requires a precise understanding of fundamental electrical terminology as defined by the National Electrical Code, NEC, which is the governing standard for this certified electrical contractor, CEC, exam. Misinterpreting these definitions can lead to incorrect installations, safety hazards, and non-compliance with code requirements, all of which carry significant legal and professional repercussions. The challenge lies in distinguishing between closely related terms that have distinct meanings and implications under the NEC. The correct approach represents best professional practice because it demonstrates a thorough grasp of the NEC's definitional framework. Adhering to these precise definitions ensures that electrical installations are safe, reliable, and meet all legal and code mandates. This meticulous attention to detail is a hallmark of a competent and responsible electrical contractor, safeguarding both the public and the contractor's professional reputation. An incorrect approach that fails to distinguish between a system and a circuit, as defined by the NEC, is a significant regulatory failure. The NEC defines these terms with specific scopes and purposes. A system is a broader concept encompassing interconnected components, while a circuit refers to a specific path for current. Applying the requirements for one to the other would lead to improper equipment selection, installation methods, and potentially unsafe conditions, violating NEC Article 100 and other relevant sections. Another incorrect approach that confuses grounded with grounding electrode conductor represents a critical ethical and regulatory failure. Grounded refers to the intentional connection of a circuit or equipment to earth, a safety measure. The grounding electrode conductor is a specific conductor that connects the grounded conductor of the premises wiring system to the grounding electrode. Misunderstanding this distinction can lead to inadequate fault current paths, rendering safety systems ineffective and creating severe shock hazards, a direct violation of NEC Article 250. Finally, an incorrect approach that conflates enclosure with raceway is a regulatory failure. An enclosure is a cabinet, box, or housing that protects electrical equipment from the environment and prevents contact with live parts. A raceway is a channel designed expressly for holding conductors or cables. Using an enclosure where a raceway is required, or vice versa, would compromise the integrity of the wiring system, expose conductors to damage, and violate NEC Article 300 and others governing wiring methods. Professional decision-making in such situations requires a systematic approach. First, identify the core terminology in question. Second, consult the NEC Article 100 definitions for the precise, legally binding definitions. Third, understand the practical implications of each definition for installation and safety. And fourth, apply the correct definition to the specific context of the installation to ensure compliance and safety. Question 13. Assessment of the appropriate wiring methods and equipment selection for an electrical installation within an area identified as having a Class I, Division 1, Group D hazardous atmosphere, considering the potential for ignition from electrical arcs or hot surfaces. Option A. Install explosion-proof enclosures and fittings specifically rated for Class I, Division 1, Group D, utilizing threaded conduit with appropriate sealing fittings. Option B. Employ standard conduit and junction boxes, relying on the infrequent presence of flammable vapors to mitigate risk. Option C. Install wiring and flexible conduit with standard non-explosion-proof junction boxes, assuming the low voltage of the system provides inherent safety. Option D. Utilize standard watertight enclosures and conduit, ensuring all connections are tightly sealed to prevent vapor ingress. The correct answer is A. Install explosion-proof enclosures and fittings specifically rated for Class I, Division 1, Group D, utilizing threaded conduit with appropriate sealing fittings. Explanation. Scenario analysis. This scenario presents a professional challenge because the presence of flammable vapors in an industrial setting necessitates strict adherence to safety regulations to prevent catastrophic ignition. The contractor must not only understand the theoretical requirements for wiring in hazardous locations, but also apply them practically, considering the specific environment and potential risks. Misinterpretation or deviation from these requirements can lead to severe consequences, including fires, explosions, injury, or death, and significant legal and financial repercussions. Correct approach analysis. The correct approach involves a thorough risk assessment that prioritizes the selection of explosion-proof enclosures and fittings specifically rated for the identified hazardous location classification, e.g., Class I, Division 1 or 2, Group C or D. This aligns directly with the National Electrical Code, NEC, requirements for hazardous locations, particularly Article 500 and subsequent articles detailing specific installation methods and equipment. The NEC mandates that equipment used in these areas must be designed and tested to prevent ignition of the surrounding atmosphere. This approach represents best professional practice because it directly addresses the fundamental hazard by containing any potential sparks or heat within the enclosure, thereby preventing ignition. It is a proactive measure rooted in established safety standards and regulatory mandates. Incorrect approach is analysis. One incorrect approach involves assuming that standard electrical enclosures are adequate if they are simply sealed against dust or moisture. This fails to address the primary hazard of flammable vapor ignition. Ethically and regulatorily, this is a failure because it ignores the specific requirements of hazardous locations, which demand equipment designed to contain explosions, not just resist environmental ingress. Another incorrect approach is to rely solely on the visual appearance of existing wiring, without verifying its suitability for the hazardous classification. This is a critical regulatory failure, as it bypasses the necessary due diligence and documentation required to confirm compliance. The NEC requires specific types of wiring methods and equipment for each hazardous location classification, and visual inspection alone is insufficient to determine this. A third incorrect approach might be to install equipment that is rated for a less hazardous location, e.g., Division 2, in an area that is classified as more hazardous, e.g., Division 1. This is a direct violation of the NEC's hierarchical protection requirements and represents a significant ethical lapse in prioritizing safety over convenience or cost. Professional reasoning. Professionals should approach wiring in hazardous locations by first meticulously identifying the specific hazardous location classification, class, division, group, based on the materials present and their properties. This is followed by a comprehensive review of the relevant NEC articles, primarily Article 500 onwards, to determine the required equipment types, wiring methods, and installation practices. A thorough risk assessment should then inform the selection of explosion-proof or intrinsically safe equipment that is appropriately rated for the identified classification. Documentation of the assessment, the chosen equipment, and the installation methods is crucial for demonstrating compliance and ensuring future maintenance is performed correctly. Question 14. Comparative studies suggest that electrical contractors often face challenges in accurately determining feeder requirements for new commercial installations. When faced with a scenario requiring the sizing of a feeder for a commercial space with a variety of electrical equipment and lighting, which of the following approaches best aligns with regulatory compliance and professional best practices as defined by the National Electrical Code, NEC? Option A. Calculate the total connected load by summing the nameplate ratings of all equipment, and then select a feeder conductor and overcurrent protection device that can accommodate this total, applying standard derating factors for bundling. Option B. Select a feeder conductor size based on a common industry rule of thumb for similar commercial spaces, and then choose an overcurrent protection device that is readily available and commonly used for such applications. Option C. Form a detailed load calculation in accordance with NEC Article 220, considering general lighting and receptacle loads, specific equipment loads, and applying applicable demand factors. Then, select a conductor with sufficient ampacity for the calculated load, and size the overcurrent protection device in accordance with NEC Article 240, ensuring it protects the conductor. Option D. Determine the required overcurrent protection device size based on the largest single piece of equipment's rating, and then select a feeder conductor with an ampacity equal to or greater than this overcurrent protection device. The correct answer is A. Calculate the total connected load by summing the nameplate ratings of all equipment, and then select a feeder conductor and overcurrent protection device that can accommodate this total, applying standard derating factors for bundling. Explanation. Scenario analysis. This scenario presents a common challenge for electrical contractors, determining the appropriate feeder size for new commercial installation. The challenge lies in interpreting and applying the National Electrical Code, NEC, requirements for feeder sizing, which involves understanding load calculations, conductor ampacity, and overcurrent protection, all while ensuring safety and compliance. Misinterpreting these requirements can lead to undersized feeders, causing overheating and potential fire hazards, or oversized feeders, leading to unnecessary material costs and potential inefficiencies. The contractor must balance code compliance with practical installation considerations and client budget. Correct approach analysis. The correct approach involves a thorough review of the proposed electrical loads for the commercial space, as outlined in Article 220 of the NEC. This includes calculating the general lighting and receptacle loads, as well as specific appliance and equipment loads. Subsequently, the contractor must select conductors with an appropriate ampacity rating that can safely handle the calculated load, considering the ambient temperature and any conductor bundling adjustments as per NEC Table 310, 15b, 16, and its accompanying notes. Finally, the feeder must be protected by an overcurrent protective device, OC, rated at or above the conductor's ampacity, but not exceeding the maximum allowable ampacity for the conductor size as per NEC Article 240. This methodical application of NEC feeder sizing principles ensures a safe, compliant, and reliable electrical system. Incorrect approach is analysis. One incorrect approach is to simply select a feeder size based on the sum of the nameplate ratings of all connected equipment, without applying the demand factors permitted by the NEC. This is a regulatory failure because it ignores the NEC's provisions for diversity and demand, leading to an unnecessarily oversized and costly feeder, and potentially a failure to recognize that, even with demand factors, the calculated load might exceed the conductor's capacity if not properly assessed. Another incorrect approach is to select a feeder size based solely on the overcurrent protection device rating, without verifying that the conductor's ampacity meets or exceeds the calculated load. This is a critical safety and regulatory failure. The OCT is designed to protect the conductor from overcurrent, not the other way around. If the conductor's ampacity is less than the OCT rating, the conductor could overheat and fail before the OCT trips, creating a significant fire hazard. A third incorrect approach is to rely on past experience or a rule of thumb for similar installations without performing a detailed load calculation, according to NEC Article 220. While experience is valuable, each installation is unique, and specific load characteristics must be assessed. This approach risks overlooking specific load requirements or code updates, leading to non-compliance and potential safety issues. Professional reasoning. Professionals should approach feeder calculations by first understanding the scope of the installation and identifying all potential loads. This is followed by a meticulous application of the NEC's load calculation methodologies, paying close attention to demand factors and specific equipment requirements. Conductor selection must prioritize ampacity based on the calculated load, considering environmental factors and derating. Finally, the overcurrent protection must be sized to protect the selected conductor. This systematic, code-driven process ensures safety, compliance, and economic efficiency. Question 15. Stakeholder feedback indicates a concern regarding the potential for increased installation costs associated with providing a dedicated grounding system for a new suite of sensitive laboratory equipment. The client is questioning the necessity of a separate grounding electrode system for this equipment, suggesting that the existing building's grounding infrastructure should suffice to save on materials and labor. As the certified electrical contractor, what is the most appropriate course of action to address this feedback while ensuring compliance and protecting the equipment? Option A. Install a single shared grounding electrode system that serves both the general building loads and the sensitive electronic equipment, assuming it will provide adequate protection. Option B. Advise the client that a dedicated grounding electrode system is a mandatory requirement for sensitive electronic equipment to ensure its reliable operation and protection, as stipulated by electrical codes, and explain the risks of not implementing it. Option C. Inform the client that while a dedicated system is ideal, the existing building ground can be utilized if the client accepts the potential risks of equipment malfunction and data corruption. Option D. Proceed with connecting the sensitive electronic equipment to the existing building's main service neutral conductor, as this is a common practice for many electrical loads. The correct answer is B. Advise the client that a dedicated grounding electrode system is a mandatory requirement for sensitive electronic equipment to ensure its reliable operation and protection, as stipulated by electrical codes, and explain the risks of not implementing it. Explanation. Scenario analysis. This scenario is professionally challenging because it involves a direct conflict between a client's perceived cost-saving measure and the fundamental safety and operational integrity requirements for sensitive electronic equipment. The contractor must balance client satisfaction with their professional responsibility to adhere to established codes and best practices, ensuring the long-term reliability and protection of the client's valuable assets. Misinterpreting or neglecting grounding requirements can lead to equipment malfunction, data loss, and potential safety hazards, all of which carry significant professional liability. Correct approach analysis. The correct approach involves prioritizing the installation of a dedicated, properly sized grounding electrode system for the sensitive electronic equipment, as mandated by relevant electrical codes and industry best practices for such installations. This ensures a stable and low impedance path for fault currents and transient voltages, protecting the equipment from damage and ensuring its reliable operation. This approach aligns with the NEC National Electrical Code requirements for grounding and bonding, specifically those pertaining to sensitive electronic loads, which often necessitate more robust grounding than standard installations to mitigate electromagnetic interference (EMI) and electrostatic discharge (ESD). Adhering to these codes is not just a regulatory requirement but a cornerstone of professional electrical contracting, demonstrating a commitment to safety, quality, and client asset protection. Incorrect approach is analysis. Implementing a single, shared grounding electrode system for both the general building load and the sensitive electronic equipment, without specific consideration for the unique grounding needs of the latter, is a regulatory failure. This approach risks introducing noise and voltage fluctuations from the general building system into the sensitive equipment, compromising its performance and potentially causing damage. It fails to meet the NEC's intent for providing a clean and stable ground reference for sensitive electronics. Connecting the sensitive electronic equipment's grounding conductor directly to the building's main service neutral conductor, without a dedicated grounding electrode system for the sensitive equipment, is a significant regulatory and safety failure. This practice can create objectionable current on the grounding conductor and does not provide the necessary low impedance path for fault current or transient surges, directly violating NEC principles for effective grounding and bonding. Ignoring the client's request for a separate grounding system and proceeding with the existing building ground without a thorough assessment and documented justification is an ethical and professional failure. While the client may be seeking cost savings, the contractor has a duty to inform the client of the risks and regulatory requirements, and to provide a solution that meets the technical demands of the installation. Failing to do so constitutes negligence and a breach of professional responsibility. Professional reasoning. Professionals should approach such situations by first thoroughly understanding the specific grounding requirements for the sensitive electronic equipment, consulting relevant sections of the NEC and any manufacturer-specific installation guidelines. They should then engage in clear and documented communication with the client, explaining the technical necessity and regulatory mandates for proper grounding, including the potential consequences of non-compliance. If the client insists on a less robust solution, the contractor should clearly document their professional recommendation, the associated risks, and obtain written acknowledgement from the client that they are proceeding against professional advice. This process ensures that the contractor fulfills their ethical and legal obligations while managing client expectations. Question 16. To address the challenge of determining the appropriate branch circuit protection and conductor sizing for a newly installed, custom-built industrial welding machine that does not have standard nameplate markings for continuous load, but has a documented duty cycle, what is the most professionally sound and regulatory compliant approach for a certified electrical contractor? Option A. Use the highest amperage reading observed during a brief test run as the basis for conductor and overcurrent protection sizing, without further code reference. Option B. Rely on the general knowledge of typical welding machine requirements from previous installations, without consulting the current edition of the NEC. Option C. Consult the National Electrical Code, NECA, for specific provisions related to welding equipment and intermittent duty loads, and apply the conductor and overcurrent protection requirements outlined therein, considering the documented duty cycle. Option D. Apply standard continuous load calculation methods to the machine's apparent power draw, assuming it operates at full capacity for the entire circuit's rating. The correct answer is C. Consult the National Electrical Code, NEC, for specific provisions related to welding equipment and intermittent duty loads, and apply the conductor and overcurrent protection requirements outlined therein, considering the documented duty cycle. Explanation. This scenario is professionally challenging because it requires the electrical contractor to interpret and apply complex code requirements to a non-standard installation, ensuring both safety and compliance without resorting to simple calculations. The contractor must exercise sound professional judgment to determine the appropriate method for sizing a branch circuit for a specialized piece of equipment. The correct approach represents best professional practice because it prioritizes adherence to the National Electrical Code, NEC, as the governing standard for safe electrical installations. Specifically, it involves identifying the relevant NEC sections that address the unique characteristics of the equipment and its power requirements, even if those sections don't involve straightforward load calculations. This demonstrates a commitment to understanding the underlying principles of electrical safety and code intent, rather than just applying a formula. It ensures the circuit is adequately protected and the equipment operates reliably and safely. An incorrect approach that relies solely on general load calculation rules without considering the specific equipment's requirements is professionally unacceptable. This fails to meet the NEC's mandate for safe installations, as specialized equipment often has unique operational characteristics, e.g., intermittent duty, high inrush current, that are not adequately addressed by generic calculations. This could lead to undersized conductors or overfused circuits, posing fire hazards or equipment damage. Another incorrect approach that involves simply using the nameplate rating without consulting the NEC for specific application rules is also a failure. While the nameplate rating is a starting point, the NEC often provides specific adjustments or requirements for different types of loads or equipment that must be followed. Ignoring these specific code provisions is a direct violation of regulatory requirements. A further incorrect approach that involves guessing or using past experience without verifying against the current NEC is ethically and professionally irresponsible. Electrical codes are updated regularly to reflect new technologies and safety findings. Relying on outdated knowledge or intuition rather than current code provisions can lead to unsafe installations and potential liability. The professional reasoning process for similar situations should involve a systematic approach. 1. Thoroughly understand the equipment and its intended use. 2. Identify all relevant sections of the NEC pertaining to the equipment and its installation. 3. Consult manufacturer's instructions, which are often referenced by the NEC. 4. If ambiguity exists, seek clarification from the authority having jurisdiction or a qualified code expert. 5. Document all decisions and the basis for them. Question 17. The assessment process reveals that a contractor is tasked with replacing a blown fuse in a critical piece of industrial machinery. The original fuse was a Class CEC time delay fuse rated at 10 amperes and 600 volts. The contractor has a readily available supply of 10 ampere, 600 volt fast-acting fuses and 15 ampere, 600 volt time delay fuses. Considering the NEC requirements for overcurrent protection of industrial machinery, which fuse selection best adheres to professional practice and regulatory compliance. Option A. Install a 10 ampere, 600 volt time delay fuse as it is the correct type and rating for the application. Option B. Install a 10 ampere, 600 volt time delay fuse, ensuring the replacement matches the original type and rating. Option C. Install a 10 ampere, 600 volt fast-acting fuse, as it has the same ampere and voltage rating as the original. Option D. Install a 15 ampere, 600 volt time delay fuse to provide a greater margin of safety against nuisance tripping. The correct answer is B. Install a 10 ampere, 600 volt time delay fuse, ensuring the replacement matches the original type and rating. Explanation. This scenario is professionally challenging because it requires the certified electrical contractor, CEC, to make a critical decision regarding fuse selection for a specific application, directly impacting the safety and reliability of the electrical system. Misinterpreting fuse types, ratings, or applications can lead to equipment damage, fire hazards, and potential injury or loss of life, all of which carry significant legal and ethical ramifications for the contractor. The contractor must demonstrate a thorough understanding of the National Electrical Code, NEC, and the specific operational characteristics of the equipment being protected. The correct approach represents best professional practice because it prioritizes safety and code compliance above all else. Selecting a fuse based on its appropriate type, e.g., time delay VS, fast-acting, and rating, ampere and voltage, that precisely matches the load's requirements, and the circuit's protection needs ensures that the fuse will operate as intended under fault conditions, preventing damage and mitigating hazards. This aligns with the CEC's ethical obligation to perform work in a manner that protects the public and adheres to established industry standards and legal requirements, as mandated by the NEC. An incorrect approach of selecting a fuse solely based on its availability or a perceived cost-saving measure is a significant regulatory and ethical failure. This demonstrates a disregard for the NEC's specific requirements for overcurrent protection, which are designed to prevent fires and protect equipment. Furthermore, choosing a fuse with an incorrect rating, either too high, failing to provide adequate protection, or too low, leading to nuisance tripping, violates the fundamental principles of electrical safety and can lead to equipment failure, potential arc flash incidents, and code violations. Another incorrect approach, such as using a fuse type not intended for the specific load characteristics, e.g., using a fast-acting fuse on a motor that experiences inrush current, will result in premature fuse failure and inadequate protection, creating a hazardous condition and violating the NEC's intent for proper overcurrent device application. Professional reasoning in such situations involves a systematic process. First, thoroughly understanding the load's operating characteristics, including normal operating current, starting current inrush, and potential fault currents. Second, consulting the NEC, specifically Article 240 overcurrent protection, and relevant articles for specific equipment, e.g., motors, transformers, to determine the appropriate fuse type and rating requirements. Third, verifying that the selected fuse meets or exceeds the voltage rating of the circuit and is listed for the intended application by a recognized testing laboratory. Finally, documenting the selection process and the rationale behind it, ensuring transparency and accountability. Question 18. Benchmark analysis indicates that during the installation of a large-scale cable tray system, an experienced electrician proposes a minor adjustment to the support spacing for a section of the tray, claiming it will expedite the installation process without compromising the system's integrity. As the certified electrical contractor overseeing the project, what is the most appropriate course of action to ensure compliance with regulatory requirements and professional standards? Option A. Reject the proposed adjustment outright, insisting on strict adherence to the original approved drawings to avoid any potential for non-compliance, regardless of the proposed change's technical merit. Option B. Immediately approve the proposed adjustment as the electrician is experienced and the change is minor, prioritizing the project's timeline and efficiency. Option C. Conduct a thorough review of the proposed support spacing against the cable, tray manufacturer's load tables, and the applicable electrical code requirements for maximum allowable spans, and if found compliant, document the deviation and seek approval from the engineer of record before proceeding. Option D. Proceed with the proposed adjustment without further consultation, assuming the electrician's judgment is sufficient, and update the as-built drawings at a later date. Correct answer is C. Conduct a thorough review of the proposed support spacing against the cable tray manufacturer's load tables and the applicable electrical code requirements for maximum allowable spans, and if found compliant, document the deviation and seek approval from the engineer of record before proceeding. Explanation. This scenario presents a common challenge for certified electrical contractors, balancing project efficiency with strict adherence to safety and installation standards when faced with a seemingly minor deviation from approved plans. The professional challenge lies in assessing the actual impact of the proposed change on the integrity and safety of the cable tray system, rather than simply rejecting it outright. A thorough understanding of the relevant electrical codes and standards is paramount to making an informed decision that prioritizes safety and compliance. The correct approach involves a detailed review of the proposed modification against the applicable electrical code requirements for cable tray systems. This includes verifying that the altered support spacing does not exceed the maximum allowable span for the specific type and size of cable tray, nor the weight of the cables it will support, as stipulated by the relevant standards. It also requires confirming that the modification does not compromise the structural integrity of the tray, create pinch points for cables, or impede future maintenance. This methodical, code-driven assessment represents best professional practice because it directly addresses the safety and performance aspects mandated by the regulatory framework. It ensures that any deviation, even if seemingly minor, is evaluated for its potential impact on the overall electrical installation's reliability and safety, thereby upholding the contractor's ethical and legal obligations. An incorrect approach would be to approve the modification solely based on the installer's assurance that it looks fine or won't cause problems. This bypasses the critical step of verifying compliance with established standards and codes. The regulatory failure here is a direct violation of the duty to install electrical systems in accordance with approved plans and applicable codes, which are designed to prevent hazards. Ethically, it represents a dereliction of professional responsibility to ensure the safety of the installation and its users. Another incorrect approach is to reject the modification without any technical assessment, simply because it deviates from the approved drawings. While adherence to approved plans is important, professional judgment requires evaluating whether a deviation, if properly assessed and deemed compliant with codes, can be accepted. Unnecessary rigidity can lead to project delays and increased costs without a corresponding increase in safety or compliance. The failure here is a lack of professional discretion and an inability to apply code knowledge to a practical situation, potentially hindering efficient project execution without a valid safety or compliance reason. A third incorrect approach is to implement the modification without documenting the change and obtaining necessary approvals. Even if it appears compliant, this creates a discrepancy between the as-built condition and the approved documentation, which can lead to significant issues during future inspections, maintenance, or troubleshooting. The regulatory failure is in maintaining accurate records and adhering to the change management process, which is crucial for the life cycle of an electrical installation. Ethically, it undermines transparency and accountability. The professional decision-making process for similar situations should involve 1. Understanding the proposed deviation. 2. Consulting the relevant electrical codes and manufacturer's specifications for cable tray systems. 3. Assessing the potential impact on structural integrity, cable protection, and accessibility. 4. Documenting the assessment and any proposed changes. 5. Obtaining necessary approvals from the engineer of record or relevant authority if the deviation is significant or impacts code compliance. 6. Ensuring all changes are accurately reflected in as-built drawings. Question 19. Quality control measures reveal that a contractor has proposed to size the electrical service for a new retail store by using the square footage of the space and applying the general lighting and receptacle load calculations typically used for a single-family dwelling, citing that the store will have similar lighting and outlet density. Option A. The contractor can estimate the load based on the square footage and a general understanding of typical retail power consumption without a formal NEC calculation. Option B. The contractor may use the residential calculation method if the lighting fixtures and receptacle types are identical to those found in a residential setting. Option C. The contractor should perform a load calculation specifically for commercial occupancies as outlined in the National Electrical Code, NEC, considering the unique load requirements and demand factors applicable to retail spaces. Option D. The contractor's approach is acceptable as long as the total calculated load does not exceed the capacity of the existing electrical service. Correct answer is C. The contractor should perform a load calculation specifically for commercial occupancies as outlined in the National Electrical Code, NEC, considering the unique load requirements and demand factors applicable to retail spaces. Explanation. Scenario analysis. This scenario presents a common challenge in electrical contracting, where a perceived shortcut in load calculation for a commercial space could lead to significant safety and compliance issues. The professional challenge lies in balancing efficiency with adherence to established safety standards and codes, particularly when faced with pressure to expedite a project or reduce perceived costs. The contractor must exercise sound judgment to ensure the installation is safe, reliable, and compliant with all applicable regulations. Correct approach analysis. The correct approach involves a thorough and accurate application of the National Electrical Code, NEC, load calculation methods for commercial occupancies. This ensures that the electrical system is designed to safely handle the anticipated electrical demand, preventing overloads, potential fire hazards, and equipment damage. Adhering to the NEC is not just a regulatory requirement but a fundamental ethical obligation to protect life and property. Specifically, understanding and correctly applying NEC Article 220, Part Roman 3, Commercial Occupancies, is paramount. This includes considering general lighting, receptacle loads, and specific appliance or equipment loads based on the occupancy type and square footage, as well as applying demand factors where permitted. Incorrect approaches analysis. One incorrect approach would be to estimate the load based on the existing service size of a previous, dissimilar occupancy. This is a regulatory failure because it bypasses the mandated NEC load calculation procedures, which are designed to account for the specific electrical needs of the new occupancy. It is ethically unsound as it prioritizes expediency over safety and compliance. Another incorrect approach would be to apply residential load calculation methods to a commercial space. This is a significant regulatory failure because the NEC provides distinct calculation methodologies for different occupancy types due to their vastly different load characteristics and usage patterns. Residential calculations are not designed to handle the higher and more diverse loads typically found in commercial environments, leading to an undersized and unsafe electrical system. A third incorrect approach would be to rely solely on the nameplate ratings of major equipment, without considering the NEC's demand factors and other calculation nuances. While nameplate ratings are important, the NEC often allows for the application of demand factors to reduce the calculated load, reflecting the fact that not all equipment operates at its maximum rating simultaneously. Ignoring these provisions can lead to an unnecessarily oversized and costly installation, but more critically, a failure to correctly apply the NEC's load calculation principles can still result in an unsafe system if the overall calculation is flawed. Professional reasoning. Professionals should always prioritize code compliance and safety. When faced with a load calculation for a new commercial occupancy, the decision-making process must begin with identifying the correct NEC article and part applicable to that occupancy. This involves consulting the NEC directly and understanding the specific requirements for general lighting, receptacle loads, and any specialized equipment. If there is any ambiguity, consulting with a qualified electrical engineer or the local authority having jurisdiction, OJ, is a critical step. The process should always involve a documented calculation that can be reviewed and verified, ensuring that the installed system is safe, code compliant, and meets the operational needs of the client. Question 20. Consider a scenario where a certified electrical contractor is tasked with supplying power to a portable, heavy-duty drill press in a commercial workshop. The workshop environment is known to have potential for oil drips and moderate mechanical abrasion from nearby equipment. The contractor is evaluating the flexible cord to be used for connecting the drill press to a receptacle. Which of the following approaches best ensures regulatory compliance and professional safety standards? Option A. Use a flexible cord rated for outdoor use only, as it is likely to be more durable than indoor cords. Option B. Select a flexible cord specifically rated for oil resistance, heat resistance, and water resistance, and ensure it is properly supported with strain relief at both ends, avoiding any conditions that could lead to crushing or abrasion. Option C. Utilize a standard, general-purpose portable appliance cord, assuming it will be sufficient for the moderate workshop conditions. Option D. Extend the drill press's existing cord with a standard household extension cord, ensuring the connection is secured with electrical tape. The correct answer is B. Select a flexible cord specifically rated for oil resistance, heat resistance, and water resistance, and ensure it is properly supported with strain relief at both ends, avoiding any conditions that could lead to crushing or abrasion. Explanation. This scenario presents a common challenge for electrical contractors, ensuring the safe and compliant use of flexible cords in an environment where they might be subjected to conditions beyond their intended design. The professional challenge lies in accurately identifying the specific type of flexible cord required for the intended application, considering potential hazards like abrasion, moisture, and heat, and then ensuring its installation adheres strictly to the applicable electrical code. Failure to do so can lead to premature cord failure, electrical hazards, and potential fire risks, all of which have significant safety and legal ramifications. Correct approach involves a thorough understanding of the National Electrical Code, NEC, requirements for flexible cords, specifically Article 400. This article details the types of flexible cords, their intended uses, and the limitations on their application. For a portable appliance used in a workshop environment with potential for mechanical damage and exposure to oil, the contractor must select a cord rated for such conditions, such as an oil-resistant, heat-resistant, and water-resistant type, E, G, SU, or similar designation. This selection ensures the cord's insulation and jacket can withstand the anticipated stresses, maintaining its integrity and preventing electrical hazards. Adhering to the NEC's provisions for strain relief, proper termination, and avoiding conditions that could lead to abrasion or crushing is paramount for best professional practice. An incorrect approach would be to use a general-purpose cord, e.g., SJT, without considering the workshop environment-specific hazards. This fails to meet the NEC's requirement for selecting cords suitable for the conditions of use and the specific type of appliance. Regulatory failure here is a direct violation of NEC Article 400, which mandates that flexible cords be used only in accordance with their listing and the conditions of use specified in the code. Ethically, using an inappropriate cord compromises the safety of the end user and the integrity of the electrical installation. Another incorrect approach would be to simply extend the existing cord with a standard extension cord without evaluating the suitability of the extension cord for the workshop environment or ensuring proper strain relief and protection. This bypasses the fundamental requirement to select the correct cord type for the application and introduces potential points of failure. The regulatory failure is again a violation of NEC Article 400 and potentially other articles related to appliance connections and cord protection. The professional reasoning process for such situations should begin with a comprehensive site assessment to identify all potential environmental hazards. This should be followed by a thorough review of the appliance's power requirements and the intended use. Consulting the NEC, specifically Article 400, and any relevant manufacturer's instructions, is the next critical step to determine the appropriate cord type and installation methods. If there is any doubt, seeking clarification from the authority having jurisdiction or a qualified electrical engineer is a prudent measure. The ultimate goal is to ensure the installation is not only code compliant, but also safe and durable for the intended application.